Welcome students to the MOOC series of lectures on non-parametric statistical inference. This is lecture number 3. In the last class, we had already discussed two non-parametric tests for centrality. In particular, we have studied one sample sign test and one sample Wilcoxon signed rank test. In this class, we shall see extension of the above two as follows. We shall first study paired sample test and also we will look at test for comparing the central location for two different populations. That means two sample test. For sign test, we are testing if m is equal to m naught and there may be three alternatives, m less than m naught, when the rejection criteria is that n plus is less than t alpha. If m is greater than m naught, that means that n minus is less than t alpha, and if m is not equal to m naught, then either of n plus or n minus is less than the corresponding critical values t alpha by 2. Why? Because these are two-sided test. We have given you the explanation before. So, if it is a one-sided test of size alpha, then we have to look at if the value is coming out to be beyond the t alpha, so that we can reject. This is for upper side. If it is lower sided, one-tailed, then we will look at this and the value should fall here in order to reject the null hypothesis. But when it is two-sided test, for equality of two end populations, this is t alpha by 2 and this is also t alpha by 2, and we will reject null hypothesis if the obtained statistic falls here or falls here. Similarly, for Wilcoxon signed rank test, we have the rejection criteria if t minus is less than t alpha or t plus is less than t alpha, or for two-sided case, we will look at if any one of them is less than t alpha by 2 or t plus greater than t alpha by 2, depending upon whether you are doing at lower side or upper tail of the distribution. Now, the same test can be used for paired sample test as well. Natural question is, what is paired sample test? So, let me first illustrate that. Typically, a paired sample test is used for comparing two population means where data consists of two samples, in which observations in one sample can be paired with observations in the other sample. Okay? Typically, both the observations are on the same sample unit. For example, before and end observations on the same subjects, such as effect of some specific diet on children's growth, or effect of a drug in lowering blood sugar, or effect of a course on a candidate's programming skills. Why these are called paired sample test? Because in all these cases, we look at a subject and we see, say for example, the blood sugar case, before administration of the drug, what is the value, and after administration of the drug, what is the value. So, this is the difference which may be considered the effect of the drug, and then we need to see whether this effect is significant or not. So, that is why these are called paired sample test, and recall that for parametric case we use paired test for paired t test for such situations, but t test assumes normality of the data. When we do not have that assumption, then we cannot use t test, and therefore, we have to go for non-parametric testing of hypothesis, and in particular we want to use the same sign test and same Wilcoxon signed rank test on the data which is coming from paired samples. So, consider a random sample of pairs x 1 y 1, x 2 y 2, x n y n. For this sample, n differences can be calculated. Di is equal to xi minus yi. That means what it was before and what it was after. So, that gives you the difference, and then the test statistic is based on the median of the difference of the paired observations. So, I hope the concept is clear. Earlier we were looking at sign test or signed rank test for either x or y. Now, since we have paired values, we look at the difference and we are going to apply the same technique on the DIs. So, what we will do in a paired sample sign test? If the population of paired differences satisfies the assumptions of underlying sign test, right? What is that? The distribution is continuous and the sample is random. If these two assumptions are satisfied, then we are going to use paired sample sign test, where the H naught or the null hypothesis is that median of the DIs is D0 or D naught versus median of the DIs is not equal to D naught. So, for example, we are looking at only two-sided test. If in addition to that, we can also assume that the differences are symmetric, then we can use paired samples Wilcoxon signed rank test, and then D1, D2, Dn are the given samples. We may test if they are coming from a population with median is equal to 0, or they are coming from a population with a median is equal to D naught. In the latter case, we have to further modify the data as follows. When the H naught is that median is equal to 0, then there is no problem, because that is typically the case. But if D naught is not equal to 0, then we shall look at xi minus yi minus D naught, and then we will check if there is any. So, that it now becomes 0 centered, and then we can test the null hypothesis. So, suppose there are 9 boys are given some nourishment, and suppose their weights before the course are this 40, 42, 35, 38, 39, 45, 28, 31 and 37. Now, after the course is complete, their weights are measured again, and we found this is the weight after the course is done. The boy with 40 has now become 42 with weight, the boy with 35 now has a weight gain 39, and similarly the one with 37 now has a weight 36.5. So, we are looking at yi minus xi, that is the gain after the nourishment course. So, we find that the difference is plus 2, plus 5, plus 4, plus 3, minus 2, minus 1, plus 4, plus 3 and minus 0.5. Therefore, our focus of attention is now this vector when we put them in sorted order of magnitude. Minus 2, minus 1, minus 0.5, these are the negative gains, and plus 2, plus 3, plus 3, plus 4, etc. These are the positive gains. Now, H naught is MD is equal to 0, that is whether there is no gain, or in other words whether the median is equal to 0 for the difference. Therefore, the corresponding statistic is going to be n plus and n minus. We see that there are 6 of them which are positive and 3 of them they are on negative side. Therefore, we know that we have to look at binomial 9, 0.5 and we have to see the cumulative probability of n minus, and from there we should be able to decide whether to accept this or reject. When we are going for signed rank test, then in the sorted order, this is the values that we have. We are now, instead of just counting, we are giving ranks to them. The smallest one in magnitude is 0.5, therefore, it gets the rank 1. The second smallest is magnitude wise is 1, therefore, it is getting the value 2. Third highest, this and this, both of them absolute value 2. So, they should get average of 3 and 4, that is why they are getting 3.5 and 3.5. Similarly, these two are getting average of 5 and 6, these two are getting average of 7 and 8, and this one is getting the value 9. Therefore, T plus is going to be 38.5 and T minus is going to be 6.5. As you can see from here, it is 6.5, and since the sum is going to be 45, we can easily get that this is going to be 38.5. Therefore, since T minus is too small compared to T plus, we suspect that the median of D can be greater than 0. Therefore, we need to test that. So, we go back to our Wilcoxon signed rank test table. We have the value 9, and at 5% level, we have the critical value to be 8, and since our obtained value is 6.5, which is less than 8, therefore, we reject the null hypothesis. Case 2, that means that we are not accepting that m d is equal to 0, that means that we are rejecting m d is equal to 0 in favor of m d greater than 0. Now, let us look at the second case when we are looking at m d is equal to 2. Therefore, now my statistic is going to be, we are going to subtract 2 from all of them. Therefore, we are getting minus 4, minus 3, minus 2.5, 0, and then 1, 1, 2, 2 and 3. Therefore, when we are applying sign test, we are getting n plus is equal to 5 and n minus is equal to 3, because we are discarding this as it is same as the value 0, and since it is 0 centered, therefore, we discard that value 0. Now, we can see that n plus and n minus are very close, therefore, sign test cannot reject m d is equal to 2. On the contrary, suppose we are using signed rank test, then in this case again we assign the ranks to the deviations and we get these two are getting 1.5 because average of 1 and 2, these two are getting 3.5 average of 3 and 4, this is getting 5, this and this together are getting 6 and 7 average, that is 6.5, and this is the maximum one in absolute value, therefore, getting the rank 8. Therefore, if we consider T plus, it is 1.5 plus 1.5 3, 3 plus 7 10, 10 plus 6.5 is equal to 16.5 and T minus is equal to 19.5. Again, I am not going into the table to check whether we can accept or reject the null hypothesis, but we can see that T plus and T minus are very close to each other. We can say from here we cannot reject the null hypothesis m d is equal to 2. Note that m d is equal to 0 is rejected against m d is equal to 2 does not mean that the median of deviation is actually 2. It is only we are accepting that m d is against m d is equal to 2, we are going to reject m d is equal to 0. In fact, instead of 2, if we are testing against say MD is equal to 1.5 or say MD is equal to 2.25, we may find that we are still rejecting MD is equal to 0 against the corresponding alternative. Therefore, we are rejecting a null hypothesis does not mean that the alternative is true. So, instead of saying that accepting the alternative, we should say that H naught is rejected. So, this is generally true for testing of hypothesis. Even for parametric cases, it does not mean that rejection of null hypothesis in against some particular alternative actually means the value of the alternative is the correct one. So, this is about paired sample test. Now, we are going little bit ahead. We want to test the centrality of two different populations. How to do that? The basic mathematical concept here is that of linear rank statistics. I shall introduce you to linear rank statistics, but the actual mathematical property of linear rank statistic we shall study in lecture 5. So, what is linear rank statistic? Suppose we have two independent random samples x 1, x 2, x m from x population and y 1, y 2, y n drawn from another population. Their continuous distribution f x and f y respectively. We want to test if x and y have same or similar distribution. Thus, when we are comparing the distribution function of two different populations, we are trying to check if f x is equal to f y x is equal to some common distribution function f x, which is not specified to us. So, in effect we are checking if these two samples are coming from the same population. So, how we proceed? We proceed as follows. As a first step, we combine the two samples temporarily. That means, we make one array made of both x and y populations. In that array, therefore, there will be capital N is equal to small m plus small n is equal to capital N many observations, and we can assign them ranks 1, 2, 3 up to n if there is no ties. In case of ties, of course, we can take appropriate average to give the ranks, so that the total sum of ranks remains same, which is equal to 1 plus 2 plus 3 up to capital N. A functional definition of rank of an observation in the combined sample with no ties can be given with the help of an indicator variable. So, let z is equal to z 1, z 2, z n is a vector of indicator variables, where z I is equal to 1 if the ith observation is an x observation and 0 if it is an y observation. Say for example, suppose my observations are 2, 5, 6, 9 and 11, where these are x and these two are y. Therefore, z 1 is equal to z 3 is equal to z 4 is equal to 1, because first, third and fourth observations are from x. Therefore, they are getting the value 1, and z 2 is equal to z 5 is equal to 0, because these two are from y population. So, that is how we get an array of size capital N with binary values either 1 or 0, depending upon whether it is from x or from y. Of course, one can do it in the reverse way. One can give 1 values for y observations and 0 values for x observations, but in that case also the treatment is very similar. Now, the rank of an observation for which z I is an indicator is I. That means that for Z1 the rank is going to be 1, the one that is corresponding to Z2 it will have rank 2, and the one that is corresponding to Zn that will have rank n in the sorted array. A linear combination of the z values sigma ai zi I is equal to 1 to capital N, which is T n z, is called a linear rank statistic, where ai's are given constants or weights or scores. Depending upon the problem, we can change the value of ai to understand certain properties. As I have said earlier, that we will look at some such mathematical properties when we shall be in our lecture 5. For the time being, we are not going into the mathematical details, rather we shall see how we can compare the distribution of two populations or two population medians. So, what we are testing? We are testing the null hypothesis that M1 is equal to M2. That means that if M1 is the median of X population and M2 is the median of Y population, we are checking whether these two populations have the same median. But notice that having the same median does not mean that these two populations have the same distribution. We shall also have to look at the dispersion of these two populations, which we shall look at in lecture 4, which is called a scale problem. For this lecture, we are just looking at the commonality of the central locations, and our statistic is therefore appropriately defined, but our null hypothesis is that H naught M 1 is equal to M 2 or H naught D is equal to 0. That means, the difference of the two medians M 1 and M 2 is equal to 0. What can be the alternative? The alternative can be as before, it can be M 1 is greater than M 2 or D is greater than 0, M 1 is less than M 2 or D is less than 0, or M 1 not equal to M 2, D not equal to 0. With this background, we study two major tests which are called Wilcoxon rank sum test and Mann Whitney U test. In Wilcoxon rank sum test, the original data x and y are from two independent samples. We want to test whether these two populations have the same median. The only assumptions that is made is that x and y have continuous distributions. This is very important. What is the method? In Wilcoxon rank sum test, the two samples are temporarily combined and the ranks of the combined data values are calculated. And then we look at the ranks for x and y separately. So, let R x be the sum of ranks for the x samples. That means, we have m observations x 1, x 2, x m. In the pooled array, they need not be consecutive. So, maybe these are the x observations. Therefore, their ranks are not in continuity 1, 2, 3 like that. Therefore, we just consider the ranks of these observations and sum them up, that is going to give you R x. In a similar way, the observations coming from the second sample, their sum is called R y. Together they have capital N many elements, and the rank sum statistic is going to be called W, which can be R x or R y. Let me illustrate with an example. Suppose there are 5 x observations and 4 y observations. Now, we sort them together and give them the ranks. the smallest one of them is 56. So, it is getting the rank 1. The second smallest is 61, it is getting the rank 2. The third smallest is 65, but there is another 65 among the y. So, both of them are getting the rank 3.5. The fifth one, because they are taking care of 3 and 4, the fifth one is 67. So, that gets the rank 5, and in a similar way we give ranks 6, 7, 8 and 9. Therefore, R x, which are the blue ones, is the sum of these ranks, which is 5 plus 1 6 plus 2 8 plus 8 16 plus 3.5, that is 19.5, and R y is therefore going to be 7 plus 6 is 13 plus 9 22 plus 3.5 is equal to 25.5. Therefore, from this given observation we calculate R x and R y. Any one of them can be used as a statistic, but before that let us observe that the total sum of rank is going to be capital N into n plus 1 by 2, which is equal to small n plus small m multiplied by n plus m plus 1 divided by 2. This is because capital N is equal to n plus m. Therefore, R x and R y are very closely related because their sum is equal to constant. If we look at the previous one, this sum is equal to 45, and because there are 9 elements, the rank is going to be 1 plus 2 plus up to 9 is equal to 9 into 10 by 2 is equal to 45. Therefore, their sum of the R x and R y is constant for a given sample size. If the two distributions have the same central location, that is d is equal to 0, then one would expect that the two samples will be intermingled well. Now, what are going to be the alternatives? D is greater than 0, that is m 1 is greater than m 2, as we have already discussed. D less than 0, that is m 1 is less than m 2, and d is not equal to 0, that is m 1 is not equal to m 2. Now, suppose m 1 is greater than m 2. When do we think that? Most higher ranks values are expected to be from x. So, suppose this is the combined population and m 1 is bigger than m 2, then we would expect that the higher values in the combined population are coming from x. So, that we could expect the median is on this side, but if these are the only values that is coming from y, we would expect the median is going to be somewhere here. So, that is the intuition that works behind choosing the criteria. So, let us consider the sum of ranks for x, that is R x. Therefore, the statistic W is equal to sigma I z I, because we have defined z I to be the 1 when the observation is coming from x, and therefore, I z I summing over I is equal to 1 to n is going to give us the Wilcoxon rank sum statistic R x. This we have already calculated. So, corresponding to this population, our statistic is going to be R x is equal to 19.5. Now, let us observe a few interesting things, that when there are 9 observations, 5 of them are from x and 4 of them are from y, then the minimum value of R x is equal to 15. Because if there are 9 observations, the minimum value that sum of ranks will get if the first 5 of them are from x, and therefore, their ranks are going to be 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15. What is the maximum possible value? The maximum possible value is going to be when the highest 5 values are taken by x. Therefore, these are going to be 5, 6, 7, 8 and 9, and therefore, their sum is 11 plus 7, 18 plus 8, 26 plus 9 is equal to 35. Now, this is a distribution because R x can take the value 15 only in this way, but R x can take the value 20 in different ways, because suppose R x takes the values 2nd, 4th, 5th, 6th and 3rd. So, that will give us the value of R x is equal to 20, but we can also get it in the form say 1, 3, 4, 5, 7. That will also give us the value 20. Therefore, as we look at the values of the statistic R x, we shall find that it can take the values between 15 to 35 with different probabilities. I want you to check that R x is distributed symmetrically around the value 25. In a similar way, one can check that if we consider R y, then minimum value is equal to 10, when y observations are the first, second, third and fourth in the combined sorted array. The maximum value is going to be 30, because when y values are 6, 7, 8 and 9, then the sum of ranks is going to be 30, and you can check that the mean is equal to 20 and it is symmetric around that value. So, this I leave it as an exercise. Let us go forward. Under H naught, the distribution is symmetric about the mean. We shall see later that expected value of W is equal to m into n plus 1 by 2 if we consider R x to be the statistic, and variance of W is going to be m n into n plus 1 by 2. As I said, we shall prove them in lecture 5. Now, suppose H 1 is m x is greater than m y, which is true. In that case, what is going to happen? We would expect that the sample x contains more of the larger ranks. Therefore, evidence against H naught, which confirms that m x is greater than m y, is provided by the rank sum W is equal to R x, which is unusually large according to the distribution of rank sums when H naught is true. As I said, with respect to x, the smallest value is 15, but the highest value is 35. So, if the observation we find that the sum of ranks of x is coming out to be very close to 35, that means that all the highest rank things are coming from x, lower rank elements are coming from y, then we would expect that the median of x is actually bigger than the median of y. Therefore, in that case, we shall reject the null hypothesis if the statistic obtained from the population is greater than equal to some critical value. And where from we get the critical value? We get the critical value from some table. Given m and n, one can find the critical region for a specific test and can refer to Wilcoxon rank sum table tabulated for different values of m and n. I shall give you a sample of that table. Note that in that table m and n are denoted by n 1 and n 2 respectively. So, these are the sample sizes n 1 and n 2. Note that to use critical values from this table, the test statistic is the rank sum associated with the smaller sample. If two sample sizes are equal, then either rank sum can be used. So, the table that I am showing to you has been taken from this source. So, before we see the table, let me just tell you something. So, consider that you are testing at 5% level of significance. That means, alpha is equal to 0.05. Now, this can be one sided, this can be two sided. Hence, accordingly, the table has two parts. Two sided critical value for alpha is equal to 0.05 and one sided critical value for alpha is equal to 0.05. Note that the two sided critical value can also be used for one sided critical value for alpha is equal to 0.025 and one sided critical value can also be used for two sided critical value for alpha is equal to 0.1. So, basically what I am saying, suppose this is the distribution of the statistic, it is the one sided critical value for alpha. So, this is the upper side, let me call it u alpha, and this is the lower side, let me call it L alpha. Therefore, we are rejecting it for a one sided test if the statistic value is on this side or the statistic value is on this side. That is for one sided test. Therefore, if I am going to test it for two sided, then with equality of tails, if I consider this and this, then the total length or the confidence of this interval is equal to 100 minus 2 alpha. That is, if alpha is equal to 0.05, then this is going to be 90%. That is why we are saying that one sided critical value can also be used for two sided critical value for alpha is equal to 0.1. So, let us now have a look at the table. It is given that the upper part, this part is for alpha is equal to 0.25 for one tailed or alpha is equal to 0.5 for two tailed. Similarly, this side alpha is equal to 0.05 for one tailed or alpha is equal to 0.1 for two tailed. Therefore, if I am testing for m is equal to 4 and n is equal to 5, then we are looking at 5% level this value which is 27. Therefore, on the upper side, if the obtained value is bigger than 27, then we are going to reject that null hypothesis, otherwise we are going to accept the null hypothesis. So, let us look at this. M is equal to 5, n is equal to 4. We have already computed this and we have found that R x is equal to 19.5 and R y is equal to 25.5. So, at 5% level of significance, when the alternative is that the median of x is greater than median of y, then the critical value that we obtained from the table just now we have discussed is 27. Therefore, the null hypothesis is going to be rejected if the obtained value of the statistic W is greater than or equal to 27. However, we have obtained the value is 19.5. Therefore, we cannot reject the null hypothesis at this significance level alpha is equal to 0.05. Sometimes it is advocated that you take the W statistic to be the sum of ranks of the one out of x and y which has less number of observations. In our case, it was y because y has only 4 observations whereas x has 5, and we have seen that R y is equal to 25.5. Therefore, using y also we cannot reject the null hypothesis at 0.05. Now, let us look at the normal approximation. If m and n are somewhat large, say greater than equal to 10, then one can use normal approximation, because it is difficult to compute these tables for all different combinations of m and n. So, after some point we can look at from large sample theory and go for the normal approximation. So, probability W greater than small w is equivalent to probability capital Z greater than small z, where z is equal to w minus mu upon sigma, where mu is equal to the mean and sigma is the standard deviation. As I have given you the values for mean and the variance or the standard deviation, but those values we will prove again in lecture number 5. So, for example, when m is 10 and n is 12 and suppose the sum of ranks of x is 150. Question is whether we are going to accept the null hypothesis or reject that one. Since expected value of w is equal to m into n plus 1 by 2 and variance of w is equal to m n into n plus 1 by 12, therefore, mu is equal to 115 and sigma is equal to 15.17. Therefore, probability w greater than 150 after making the normalization is coming out to be probability that a standard normal random variable z is greater than equal to 2.3. Now, let us look at the normal table. We can see that probability a normal distribution is less than equal to 2.3, that value is given as 0.9893. Therefore, probability that normal variable is greater than 2.3, that value is coming out to be 0.0107. Therefore, if this is the normal distribution and this is 2.3, then this area is only 0.01. That means that the probability a standard normal variable will take a value greater than 2.3, that probability is only 1%. Now, suppose we are testing at 5% level of significance, therefore, at 5% level of significance this is going to be rejected. Let us now discuss the other important test, which is called Mann-Whitney test. The statistic that is computed here is called the U statistic or Mann-Whitney U statistic. Often people club it with Wilcoxon rank sum test, and in some literature you may find people are calling it Wilcoxon Mann-Whitney test, but you have to remember that these two tests, rank sum test and Mann-Whitney U test, are slightly different, although they are very closely related. So, we shall explore the test and then we shall see what is the relation between Mann-Whitney test and Wilcoxon rank sum test. So, suppose x 1, x 2, x n and y 1, y 2, y m are independent samples from two distributions f and g. So, here again we are testing the equality of the centrality of the two distributions f and g, where f is the CDF of x and g is the CDF of y. The U statistic is computed by comparing each element of x with each element of y. So, let me explain. So, basically what we are doing, it is the count of the number of times an y observation is less than an x observation in the combined ordered arrangement of the given two independent samples. Therefore, it is computed as u is equal to sigma over I is equal to 1 to m, j is equal to 1 to n, t x I y j, where t x I y j is equal to 1 if y j is less than x I, and that is 0 if y j is greater than x I, where I is equal to 1 to m is the number of x samples, j is equal to 1 to n is the number of y samples. Now, you may question what happens if y j is equal to x I. So, typically we discard such things, because under the null hypothesis the two samples come from continuous distributions. Therefore, the possibility that x I is equal to y j for some I j need not be considered. But in reality we may get some such data. Therefore, we discard both of them from the two populations in our subsequent computation, and accordingly the values of m and n need to be adjusted. Therefore, if we look at it, we are checking m n many pairs, because each x observation will be compared to all the y observations and vice versa. Now, question comes, what is the relationship between Wilcoxon rank sum statistic W and Mann Whitney U statistic? Suppose W is the sum of ranks of x observations in the pooled population. Therefore, W is equal to R x, which is the sum of ranks of the x observations. So, we can write it W is equal to I is equal to 1 to m or I. This R I denotes the rank of the ith x observation in the combined sample. Therefore, what is R I? That is the rank of the ith x sample. This is going to be the number of y j that is less than x I plus rank of x I among the x values. Therefore, the sum of R I is equal to summation over T x I y j, I is equal to 1 to n, j is equal to 1 to n, T x I y j plus sum of rank of x I among the x's. Now, among the x's we have m observations. Therefore, the sum of ranks is going to be m into m plus 1 by 2, and therefore, this element, which is nothing but the u statistic, is coming here, and from here we can find that the relationship is that W is equal to u plus m into m plus 1 by 2. So, let me give you an example here. Consider x is equal to 78, 66, 68 and 72, that is there are 4 observations. Therefore, m is equal to 4, y is equal to 65, 76, 61, 67 and 56. Therefore, n is equal to 5. Now, in the combined population, when we arrange them in sorted order, it looks like this, of which the blue ones are x observations and their ranks in the combined population are 4, 6, 7 and 9. Therefore, the Wilcoxon rank sum statistic W is equal to 4 plus 6 plus 7 plus 9, which is equal to 26. What is U statistic? We are checking how many y's are less than each x. Therefore, we are comparing 1, 2, 3, 4, 5, all 5 of y's with 66, 68, 72 and 78. That is, effectively we are comparing 20 pairs of observation, but from this sorted array we can easily count that there are 3 y's which are less than 66, thus I get a 3. There are 4 y's 1, 2, 3 and 4 which are less than 68, same 4 are also less than 72 and all 5 y's are less than 78. That is why the U statistic is equal to 3 plus 4 plus 4 plus 5 is equal to 16. Therefore, we can see that W is equal to U plus 1 plus 2 plus 3 plus 4, because the sum of ranks of x elements within themselves are going to be 1, 2, 3, 4, that is U plus 4 into 5 by 2, which is equal to 10, therefore, 16 plus 10. Hence, we verify that relationship between W and U, that W is equal to U plus m into m plus 1 by 2. Now, note that U is equal to 0 if all yj's are greater than xi's. That is pretty obvious, because if xi's are this and y's are this, then all xi is less than yj, there is not a single instance when an y observation is less than an x observation. Therefore, the value of the summation is going to be 0. On the other hand, if all the x's are greater than all the yj's, therefore, for all the m into n many pairs, we will get a score 1 and thus we shall get the value m n. Therefore, U tends to be smaller if all yj's tend to be larger than the xi's. Hence, mostly f z is going to be greater than g z, that is y is stochastically larger than x. Here f is the CDF of x and g is the CDF of y. Similarly, if u is larger, then y is stochastically smaller than x and therefore, g z is greater than f z for all z belonging to R. So, let me explain this with a diagram. Suppose g z is the distribution of y and suppose it has a shape like this. We know that each distribution function at minus infinity is going closer to 0 and at plus infinity it is going towards 1. So, let us call it g z. Now, g z is greater than f z for all z. Therefore, how will f z look like? It will look like something like this. Although eventually it is also going to touch 1, but in most of the values for the real number z, we can see that g z is greater than f z. So, let us call it f z. Therefore, what we can say? We can say that given any particular value of z, say this one, the g z is greater than f z. Therefore, the proportion of y values is bigger than the proportion of x values which are less than equal to z. Therefore, most of the x values are going to happen on the other side of z, that is on this side we shall get more x values than y values. That is why we say that y is stochastically smaller than x if g z is greater than f z. Similarly, as we have seen in the previous slide that f z is greater than g z implies y is stochastically larger than x. Therefore, the test that we want to do is whether they have the similar distribution, that is f is equal to g, then u should be close to m n by 2, because that is the average value, because the range of u is from 0 to m n, and therefore, what we can see that the average value will come to be m n by 2. The further it is from the central value, the more is the chance that null hypothesis is going to be rejected. Therefore, depending upon the alternative, the rejection criteria will change. For example, if alternative is f is greater than equal to g, then that means that y has more spread than x, that means that y is stochastically larger than x, then we shall reject the null hypothesis if u is too small. Similarly, if the alternative is f is less than equal to g, then we shall reject the hypothesis, null hypothesis, if u is too large, that is u is greater than equal to some critical value. On the other hand, if we have a two-sided alternative, then we should check whether u is too small or too large, that is it is greater than some threshold or less than some other critical value, and based on that we will be rejecting the null hypothesis. These critical values are calculated manually using difference equations, which we are not going to discuss here, but let me tell you a practical way of using this. The table of critical values is available, which is called Mann Whitney test, but for practicality we actually compute two different statistics, let them be u 1 and u 2, where u 1 is the one that we have already discussed, t x I y j, where t x I y j is equal to 1 if y j is less than x I. Therefore, here we are checking how many y j's are less than how many x i's. So, that gives us the statistic u 1. Now, let us consider u 2 is equal to sum over I and j 1 minus t x I y j. Note that if t x I y j is equal to 1, then this value is equal to 0, and if t x I y j is equal to 0, then this value is coming out to be 1. Therefore, effectively this counts how many x i's are less than how many y j's. Therefore, when we calculate u 1 and u 2, we take the minimum of them and we call that the u statistic. So, for a significance level alpha, for one-tailed alternative hypothesis, the critical value C alpha is the left-tailed critical value. We will check if it is smaller than some critical value C alpha or not, and that is what we want to test. For H 1 is equal to f is not equal to g, then we shall check in a two-tailed alternative hypothesis in a very similar way. So, let us look at the Mann Whitney U statistic. For two-tailed, the values are given for different values of m and n, which are given n 1 and n 2 respectively. In our case, similarly, there is one-tailed testing, so that the value for different m and n is given for one-sided test, and the alpha are taken to be 0.05 and 0.01. So, let us revisit the example. We have this is the sorted value. We have already calculated R x is equal to 26. U 1 is coming out to be how many y's are less than x. This also we have computed to be 16. I am not repeating that, but in a similar way U 2 is going to be, this is going to be 0 for this, because no x is smaller than this y, 0 for this, 0 for this. Therefore, we got 3 zeros. It is going to be 1 for 67, because there is an x value smaller than this, and this is going to be 3 for 76, as there are 3 x values smaller than this. Therefore, the value of the statistic is 4. Hence, Mann-Whitney U statistic is equal to minimum of 16 and 4 is equal to 4. So, suppose we are now looking at one tilt critical value for alpha is equal to 0.5. If we go back to the table for one tilt for 0 and 5, the value at 5% level is given out to be 2. Therefore, since u is greater than 2, we do not reject the null hypothesis. For a relatively large values of m n, critical values may be difficult to compute. Hence, one may use normal approximation with mean and variance is equal to m n by 2 and m n into n plus 1 by 2 respectively. This can be computed from mean and variance of w is equal to R x, which is the Wilcoxon rank sum statistic. How we compute? Expected value of w is equal to expected value of u plus m into m plus 1 by 2, which is expected value of u plus m into m plus 1 by 2. Now, we have already stated that, although we did not prove it yet, that expected value of w is equal to m into capital N plus 1 by 2 implies expected value of u is equal to m into capital N plus 1 by 2 minus small m into m plus 1 by 2, which comes out to be m n by 2. Variance, I have calculated it, but actually one does not need to calculate explicitly, because we know that the relationship between w and u are w is equal to u plus m into m plus 1 by 2. Therefore, because it is a constant, we know that variance and w and variance of u are going to be the same. Therefore, we can see that same value of variance will come here, which is m n into n plus 1 by 2. Therefore, we can use the fact that u minus mu divided by sigma is approximately standard normal to find the related p values and critical regions. Okay, friends, I stop here today. So, in this class we have studied two important non-parametric tests, namely Wilcoxon rank sum test and Mann-Whitney test. These are used for testing the equality of the central location of two different populations. But as I said at the very beginning, that when we compare two different distributions, we not only look at the centrality, we also look at the dispersion. Therefore, it is not enough to check the medians of the two samples, we should also check whether their dispersions are also same nature or not, or whether we can accept that they have the same level of dispersion. The corresponding problem is called the two sample scale problem. In the next class, we shall start with this. Okay, friends, I stop here today. Thank you.